to my limits series. Today, we will focus on another property of limits. In this case, a property of taking a product of two functions. Specifically, the limit of the product of f of x times g of x is equal to the limit of f of x times the limit of g of x. As with my previous limit properties videos, we have to make an assumption here. And that assumption is the idea that these two limits exist. So to write that formally, again, I will write it on the board here. So for f of x, we can say there exists a real number L such that the limit as x approaches x naught of f of x is equal to L. And basically this is just another way of saying that this limit exists. Let's call that limit L. And for g, we can say, well, there exists an m, right, such that the limit as x approaches x naught of g of x is equal to m. So now, let's use the definition of these limits to see what we can show. Starting with our first limit, we know for all epsilon greater than 0, there exists a delta greater than 0, which we will call delta A, such that for all x, right, whenever x is within delta of x naught, so the distance between x and x naught is less than delta, right, this implies that the distance between our function and our limit, so f of x minus L, is less than epsilon. This is pretty standard stuff. And for this less than epsilon, we might modify this a little bit, but we can get to that later. Now, we also know, right, that there exists an m, that's a real number, such that the limit as x approaches x naught of g of x is equal to m. And this means the following. Right, for all epsilon greater than 0, there exists a delta, which we will call delta b. It's also greater than 0. And then whenever x is within x naught of our delta, right, in this case it's delta b, in this first case is delta a, there is an implication here. And I'll just make sure to write this here, that g of x minus m, right, the distance between those two, is less than epsilon. Now I'm going to write what we are trying to show. And that's this. The limit as x approaches x naught of f of x times g of x is equal, right, to the product of those individual limits. So this is L, this is m, so it's L times m. And again, using our limit definition, for all epsilon greater than 0, there exists a delta, which we need to find, that's also greater than 0, such that for all x, whenever x is within delta of our x naught, that this implies that our function, which in this case is the product, minus the limit, right, L times m, is less than epsilon. So the absolute value of f of x times g of x minus L times m, whole thing in absolute values, is less than epsilon. And this statement in blue here, we have not proven yet, but we want to show. Now, in order to begin proving this limit, let's take a look at this final inequality. That being, the distance between, right, our function and our limit, in this case, is less than epsilon. So let's look at this left term, and I want to make this a little more interesting by adding sort of a fancy zero. So I'll explain what I mean by that. We have the absolute value of f of x times g of x, right? Nothing unusual there. And now I'm going to subtract f of x times m. Now, of course, we've changed what's in the absolute value, but no fear, we can add in f of x times m, right? So these two terms cancel out. So essentially, we've added 0, but it looks a little more fancy. And then we can subtract, right, our L times M. And we have the same term as we had before, now just written a little bit differently. So we have this thing in our absolute value, and let's factor some terms out to make this a little bit easier to look at. So in our first two terms, we can factor out an f of x, and in our second two terms, we can factor out an m. So we have the absolute value of f of x times g of x minus m, and then we can add to this an m times f of x minus L. Now, if you're looking at these original limit definitions, you can see that this f of x minus L and this g of x minus m that are used here might come into play. But there are a few things that we have to do first. Now, this whole thing is in absolute values, but we can use the triangle inequality to split this up. We know that in this case, this term, right, will be less than or equal to the sum of the absolute value of each term individually. So this is less than or equal to the sum of f of x times g of x minus m, and m times f of x minus L. That's all in absolute values. And now, we can look at these terms on here. By a property of absolute values, we can break up each of these absolute values into the absolute value products. So I'll write that as follows. Right? The absolute value of f of x times the absolute value of g of x minus m plus the absolute value of m times the absolute value of f of x minus our L. And I'll just write an equal sign because this term, or an equal sign here, this term and this term right here are both equal. So our goal here is to show that this difference, right, between our function and our limit that I've written in blue is less than epsilon. Because of what we have written here, it is sufficient to show that this term that I've written here is less than epsilon. And because we are adding two different terms, perhaps we can show that each term individually is less than epsilon over 2. Then therefore, their sum would be less than epsilon. So let's look at this term on the right. Our goal is to show that absolute value of m times absolute value of f of x minus L is less than epsilon over 2. So we can divide by absolute value of m on both sides. So f of x minus L, that difference, is less than epsilon over 2 times the absolute value of m. However, in the case that the absolute value of m is equal to 0, then this doesn't work. But what we can do is we can just make our denominator larger, which in this case makes the term smaller. And because we're adding 1, we know that this is going to be greater than 1. So therefore, this is still going to be less than epsilon, which means that we can sort of control our difference between f of x and L to be less than this term right here. So we can write that instead of this being less than epsilon, it's less than epsilon divided by 2 times the absolute value of m plus 1. And as I've explained in my previous videos, this still works for the definition of a limit because all real numbers can be written in this form. Therefore, if epsilon represents all real numbers, then our difference being less than this term right here still lets the difference be less than any arbitrary positive real number. So now let's take a look at what we have on our left side of this term, our absolute value of f of x times the distance between g of x and m. Now we can't just do the same thing that we did with our f of x minus L because we're multiplying by a function and not by a constant. However, because we are making an assumption about this limit, right, that the limit as x approaches x naught of f of x is equal to L, we know that for values where x is close to x naught, that this distance is small. And really we only care about the small values because we're looking at values where x is going to be within x naught of delta. So we can say that not only is the distance between f of x and L less than this term here, but let's also say that it's generally less than 1. And this still fits with our definition of the limit because if it's less than all the positive real numbers less than 1, then it's still less than all the bigger real numbers as well. And it's necessary because for it to be less than all the real numbers, it must be less than all the real numbers, right, between 0 and 1. So there we go. Now we have, right, this statement that the distance between f of x and L is less than 1. And we can write that here, right, that f of x minus L is less than 1. And we want to get the absolute value of f of x by itself, right? So we can turn this into a constant. So what we can do is we can add the absolute value of L on both sides, and then use the triangle inequality, right? So f of x minus L plus L, right? Because I'm adding these two things together, all in absolute values, is less than or equal to f of x minus L, right, plus the absolute value of L. And this is less than 1 plus the absolute value of L. And therefore, by transitivity, right, these negative L and positive L cancel out. So we get the absolute value of f of x is less than 1 plus the absolute value of L. And now we know that our f of x is less than a constant. So we have our g of x minus m, that in absolute values, times our absolute value of f of x. This is less than this difference times a constant, which means we can isolate for this difference. So now we have absolute value of f of x times g of x minus m in absolute values. Right, this right here is less than 1 plus absolute value of L times the distance between g of x and m. And our goal, right, is to make this less than epsilon over 2. So now, right, we can isolate for our g of x minus m. And simply to do that, all we have to do is divide by this 1 plus absolute value of L. Which means, and I'll write this up here next to our f of x minus L, right? This means that the distance between g of x and m, therefore, is less than epsilon over 2 times 1 plus absolute value of L. And we see there are no issues when our L is equal to 0, because when L is equal to 0, we simply get epsilon over 2. Now we can look here and show that because of what our g of x is less than, or this difference is less than, and with this difference, f of x minus L is less than, we get that this is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon, which means that this term right here is less than epsilon. And this is what we would need to show to prove our limit. While I've shown a lot of the necessary math to prove the limit, I wanted to sort of restart just so I can show how we would go about formally proving this now that we have fully realized what we want our limit definitions to be. So I'll go through, and for our f of x, right, for all epsilon greater than 0, there exists a positive delta we call delta A, such that whenever x is within delta A of x naught, the distance between our function and our limit is less than the minimum between epsilon over 2 times the absolute value of m plus 1 and 1. I essentially wrapped up this whole thing being less than 1 to one term by saying that f of x minus L is less than this epsilon term only when it is less than 1. And we show, right, that, again, this is sufficient because of the definition of a limit, and we will show that this still works with our new limit we are trying to prove. Now, here, right, for all epsilon greater than 0, there exists a delta b, such that whenever x is within delta b of x naught, that implies that the distance between g of x and m is less than epsilon divided by 2 times 1 plus the absolute value of L. Now, we want to show that the limit as x approaches x naught, right? So it's the same x value of f of x times g of x is equal to L times m. And again, this implies that for all epsilon greater than 0, there exists a delta which we need to find that's greater than 0 because of the distance, such that whenever, right, 0 is less than the distance between x and x naught, which is less than delta, right, that this implies that our function, right, in this case, which is the product, minus the limit, which is the product of the previous limits, is less than epsilon. So we want to prove what I've written in blue. So the first thing we have to do is find our delta. So in this case, we suppose that delta is equal to the minimum between delta A and our delta B. And essentially what we're doing here is that we're getting access to both of the information that we get from each limit definition. If it's less than the smaller of these two deltas, it will be less than the bigger of these two deltas, based on the definition of transitivity and the fact that delta is always positive. So therefore, x minus x naught will be less than delta A, and it will also be less than our delta B. So again, we start with this term. So we have the distance between our function, which is our product, so f of x times g of x minus L times m is equal to the following. We have f of x times g of x minus f of x times m plus f of x times m minus L times m, right? This is still equal. And then this is equal again by factoring. So we have f of x times g of x minus m plus m times f of x minus L. All of that is in absolute values. And now we know, based on the triangle inequality, that we can split these two things up. So this is less than or equal to the next line. So the absolute value of f of x times g of x minus m plus the absolute value of m times f of x minus L. And based on the properties of absolute values, this is equal to absolute value of f of x times absolute value of g of x minus m plus absolute value of m times absolute value of f of x minus L. So again, notice so far, we start with our original difference, right? The one that we're trying to show is less than epsilon. And we know that based on transitivity, it's less than this. And so again, we want to show that each term here, right, is less than epsilon over 2. And this is less than epsilon over 2. So, first of all, right, we know that the distance between f of x and L is less than 1. So f of x minus L is less than 1. And so we can add absolute value of L to both sides. So again, this is the same process that I did before. And so now we know by transitivity, right, that f of x minus L plus L, which is less than f of x minus L plus absolute value of L, is less than 1 plus absolute value of L. So therefore, absolute value of f of x is less than 1 plus absolute value of L. So that is just something to keep in mind. So I've written it up here. So therefore, if f of x is less than 1 plus absolute value of L, then g of x minus m, that absolute value, all right, we can take this inequality and we can multiply by absolute value of g of x minus m on both sides. So absolute value of f of x times absolute value of g of x minus m is less than 1 plus absolute value of L times absolute value of g of x minus m. And I'll erase this because we haven't quite shown that that's less than epsilon over 2 just yet. So we know that our g of x minus m is always less than epsilon over 2 times 1 plus absolute value of L. So we know that this is less than 1 plus absolute value of L times epsilon over 2 times 1 plus absolute value of L. So this is less than epsilon over 2. So therefore, we have shown that this first term is less than epsilon over 2. Now let's do the same for the second term. Now we want to show that this right term over here is less than epsilon over 2. So we know that we want our f of x minus L. Well, we're assuming, right, that it's always less than epsilon divided by 2 times absolute value of m plus 1, right, whenever that itself is less than or equal to 1. So we can write that and say absolute value of f of x minus L is less than epsilon divided by 2 times absolute value of m plus 1. Now, of course, we can multiply both sides, right, by absolute value of m. So now this product here kind of looks like this term we have right here. And we multiply by absolute value of m. And we can see, right, that if we have, like if we were to cover this 1, that this would be equal to epsilon over 2, right? Because you would just cancel out the m's. And we're making our denominator bigger. So if we make our denominator bigger, then the whole thing is smaller. So therefore, this is less than epsilon over 2. So by transitivity, right, this term, f of x minus L times absolute value of m, is all less than epsilon divided by 2. So now we've shown that each of these terms, right, is less than epsilon over 2. So the product, or not the product, but the sum of these terms here is less than epsilon over 2 plus epsilon over 2 because we've shown each term individually is less than epsilon over 2. And that's equal to epsilon. So by transitivity, right, we have that f of x times g of x minus L times m, all that wrapped up in absolute values, must be less than epsilon. And therefore, we have proven our product property of limits.